I'd like to thank Jim Kinter for giving me a few minutes. I think I asked him for a few minutes to talk about something, which I now forget. So I'm going to use those few minutes to talk about Shukla instead, which seems to me appropriate for this symposium. And in particular, some of the non-scientific aspects of Shukla's contribution to the community, which you may or may not know about. And the first thing is Shukla in Toga. Toga, unfortunately, has been forgotten by the younger generation, but it was a program that ran from 1985 to 1995, planned as a 10-year program and actually ended as a 10-year program. I say that because Clive R, which is a 15-year program, is now in its 21st year. The Toga was a program devoted entirely to predictability, so it is not surprising that Shukla was involved. And the way he was involved was that an interesting set of advisory mechanisms was set up in the United States. The Toga panel was a sub-panel of the Climate Research Committee in the United States. The Toga panel actually looked at the day-to-day and month-to-month operations of the Toga program in the United States. In any program starts off strong because the enthusiasm that occurred from the people who started the program continues on for a while, but it's that middle part that's absolutely crucial. Shukla was the chair of the Toga panel in that crucial middle part. There were only 3 chairs of the Toga panel. The 2 others are in this room. Well, actually, there was a third, but that's part of esoteric knowledge that is available only to the high priests of Toga. Shukla's contribution to the Toga program was major, and that's not surprising. The second thing I want to talk about is Shukla and the International Center for Theoretical Physics. When I was a physicist, I'd known about the International Center for Theoretical Physics. It was designed to take people from poor countries and give them opportunities in physics, and it was probably very successful for the people involved. But Shukla made a case to the head of the International Center for Theoretical Physics, a very prominent Nobel Prize winner in physics, Abdus Salam, that perhaps it might be more useful for people to come and learn something about the earth sciences, because that would be of great value to the nations that they actually came from. And he convinced Salam to start a program in earth sciences, which Shukla led, and it started by getting Antonio Mura to spend a year at the ICTP, and it actually got off the ground extremely successfully, and I am extremely grateful to it. I lectured there at least 5 times, and my memory is a little vague, but probably 6 times. And the first possibility that I saw for a book on El Nino Southern Oscillation came about through lectures at the ICTP, for which I am eternally grateful for Shukla. The third thing I want to mention is Shukla and Kola. And I don't think people really understand how truly remarkable this accomplishment was. Shukla was a professor at the University of Maryland, but had this vision of a group of people devoted entirely to predictability. As we all know who are in university departments, there are extraordinary constraints on our behavior, on our ability to do things, on our ability to hire people, and basically your life is not entirely your own, except within a very small group. But his vision was larger than that, and he did something remarkable. He decided to leave the University of Maryland and start COLA. I can't tell you how bold and courageous that truly was. I can't imagine, I certainly couldn't imagine it of myself, a university professor going out and doing something that innovative. It has turned out to be extraordinary in its impact. It was a first group that actually had everybody interested in predictability. One of the first groups that concentrated on the predictability due to the land component of the coupled ocean-atmosphere-land system, or is coupled ocean-land-atmosphere system, sorry. It's not coal, it's COLA. There are so many things that go into setting up a new institution. Part of it is getting the funding for it, and probably that's the smallest part. Part of it is setting up the infrastructure for paying people, and fortunately Anne Shukla did a lot of that with Shukla, and that was enormously valuable. And the last part is hiring all the right people, and in retrospect, Shukla hired all the right people. I think the transition of a predictability group to the university system is unprecedented, unique, and I hope it sets a standard for the future. So I will stop there and introduce our first speaker of this session. I'm the chair, so there's no questions. The first speaker will be Kathy Pegion of COLA, and she'll talk about subseasonal predictability and prediction.
You're going to get me for 30 seconds. I'm going to try and change something.
Here. Thanks, Tom. All right, well, good afternoon, everyone. I'm Kathy Pegion, and I think the best way really to introduce myself is the most recent example of the fact that no one ever really leaves COLA. I got my PhD at COLA under Dr. Shukla in 2007, and I've recently returned as faculty. And I think that is a real testament to what an amazing place COLA is, and the amazing things that Shukla has done to make such a vibrant scientific community there. So what I want to talk about are some of the lessons that I learned from Shukla and applied to my area of research, which is subseasonal predictability and prediction. So the first lesson, of course, that we all know is that there's predictability in the midst of chaos. So as an eager climate dynamics graduate student, I thought, well, there's plenty of chaos on the subseasonal timescale, so maybe I should look for some predictability there. Lesson number 2 was look to the tropical oceans. So that led me to the Madden-Julian oscillation, and wondering about the role of air-sea interactions for the MJO, and what does that mean for predictability? So just on the left here, which one of these, the top one? All right, there we go. On the left here, we see the familiar eastward propagation of precipitation anomalies associated with the MJO. And on the right, this is a lagged correlation showing the precip-SST relationship in observations, where we have warm SSTs about 10 days ahead of the MJO convection, and cool SSTs about 10 days behind that. And so then the question was really, if the ocean is involved, does that have an impact on improving the potential for predictability of the MJO? So the third lesson is use the best model you can get your hands on. So at this time, the CFS version 1 had just come out. And we, fortunately for me, Shukla, and my other committee members, knew that there was evidence that the CFS was able to represent coherent convection of the MJO. And so, of course, when they asked me, I said, sure, I can run the CFS, no problem. However, as you also know, this is an operational prediction model. It was not designed as a community model. So a bit of a challenge, but fortunately, we were able to run it. And so if you look on the left side here, you do see from the coupled CFS model, you see the eastward propagation of MJO. This is precipitation of MJO-like anomalies here. And then we also ran it in an uncoupled manner, where we forced it with the SSTs from the coupled model. And you can see that the uncoupled model is actually able to produce eastward propagation precipitation anomalies as well. We looked at the precip-SST relationship and found, of course, not surprisingly, the coupled model can reproduce the observed SST precip relationship. The uncoupled model can't quite reproduce it. So then we moved to looking at classically, and not surprisingly, as a student of Dr. Shukla was looking at predictability estimates. So what we did was a series of predictability experiments using the CFS model for the MJO, where we picked an MJO events in the long coupled simulation, perturbed those, and then ran perfect model forecast and said how well can we predict the coupled simulation. And so if you look at these predictability estimates, this is in terms of anomaly correlation. We can see the coupled model here is the black line on the top, and it's actually the top line in all 4 of these variables. And so then to see how the SSTs matter and how coupling matters, we ran the same predictability experiments, giving it perfect SSTs from the coupled simulation, forecast SSTs, sort of like a tier 2 forecast, and then some other cases such as persistent anomalies, monthly SST, and no anomalies, basically. And as you can see, the ones that have the high frequency SSTs are actually the ones that have the best predictability. So I want to point out that this was work that was done as part of my dissertation, but this is actually, MJO and RC interaction is actually still an open question. And so I'll highlight here a couple of more recent studies showing that, for example, saying that maybe AGCMs with a poor MJO, the coupling simply is providing a crutch to augment MJO-like activity. And another study here from the Dynamo experiment showing that saying that basically observational scenarios suggest the roles of RC coupling on the MJO vary greatly from event to event, because they found that only 2 of the Dynamo MJO events actually showed strong coupling. So lesson number 4 is use an ensemble prediction system. And so just as an example here, I'm showing for OLR the previous predictability experiment, predictability estimates from single members. But if you make an ensemble mean, you see that you get actually better predictability. And this is further underscored by subsequent work in which I was able to demonstrate here that you get, there's a lot of people who are saying the statistical models can do MJO just as well as dynamical models, but actually once you make a lagged ensemble from the dynamical models, you're actually able to better predict week 2 and week 3 OLR and Northern Hemisphere stream function from a lagged ensemble. And then the last 2 lessons I want to highlight are sort of ongoing and future work. And they are, don't be afraid to dream big. And I'll add, don't worry about the little things like the amount of data you have or computer time. Those things will work out. And then also connect your research with operational predictions. So more recently, I've been involved in the North American Multi-Model Ensemble Project. And I want to expand that to the subseasonal timescale. The current project is focused on monthly predictions. And this is a big task in itself because making predictions on the subseasonal timescale suddenly requires a lot more resources from computers, humans dealing with data, because you need much more frequent initializations. So I'll highlight a little bit of the work involving the subseasonal NMME. To get started on this big idea, we started with a limited scope reforecast experiment branched off from the monthly NMME project. And we just decided to see if we could demonstrate the potential for MJO prediction with the multi-model ensemble. So we have some reforecast experiments that were run by 3 different models for a subset of years. And initializations only in November in order to kind of scope down the amount of data and runs, and initialized every 5th day following the CFS2RR dates. They were run for 45 days. The atmosphere and ocean were initialized. In some of them, the land was initialized. And then we had at least 3 ensemble members from each of the models, and some did more. And so this is a very small subset of data, and the results are not particularly, because we have such a small amount of data, they're not very robust, but they are suggestive of the benefit of an NMME for subseasonal timescales. So what I'm showing here is the real-time multivariate MJO index correlation. And what this suggests is that a subseasonal NME can take advantage of differing model skill at different lead times. So what you see is the model in green here is more skillful than the blue model at early lead times, and you can see that the blue model is more skillful at later lead times. And it appears that the black line, the NME, is able to take advantage of that. The second thing we found that these runs were suggestive of is that a subseasonal NME better represents the relationship between ensemble spread and error. So we know that many of our models, the spread is too small, the models are overconfident, but we want the spread to represent the error. And we see here the difference between the RMS error in the real-time multivariate MJO index and the spread in the lighter dashed lines. And these arrows here show you the distance between the ensemble mean RMS error and the spread. And you can see that for the NMME, that distance is much smaller. And then we also find that a subseasonal NMME can provide understanding of predictability limits. So what I'm showing here, again, is the RMM index correlation skill, and then also the predictability on the top here. So this is perfect model skill. This is actual correlation. And so for the individual models, the perfect model skill is how well does the model predict itself. So you can see, for example, this red model here has higher predictability early on and it drops off. For the NMME, you see actually that the predictability is much lower. But what this is doing is saying how well do each of the models predict each other. So what I would argue is that since we know the spread is often too small in our ensembles, it's likely that we're overestimating predictability using these perfect model calculations. But using an NMME, we can actually possibly make more realistic predictability estimates. And then finally, what I want to point out is that as we move forward with this subseasonal NMME idea, we had a recent workshop to try to come up with a plan for a protocol for some reforecast experiments and doing some real-time testing. And again, this is the whole part about, I'll point out, about connecting your work with operations. We want what we're doing to really connect to and contribute to improving operational prediction. So we're going to do real-time predictions on the CPC operational schedule so that it can contribute to their product suite. So to summarize, there's predictability in the midst of chaos, and there's plenty of that on the subseasonal timescale. Look to the tropical oceans, and I'll highlight that I also learned at COLA that we have to look beyond just the tropical oceans. There's also the role of the land, as well as was discussed in the recent NMME workshop, the role of the stratosphere for these timescales. Use the best model you can get your hands on. This is an ever-moving target, but model improvements provide us a lot of potential benefit for improving prediction, so it's always prudent to stay on top of that. Use an ensemble prediction system, and we're doing that in terms of a multi-model ensemble prediction system. Dream big, so hopefully we can get this big subseasonal NMME project off the ground, and then connect your work to operational predictions as we're doing with the NMME project. Thanks.
Thank you, Kathy, for a nice summary of where to go with this subseasonal prediction question. I think I had somebody at your meeting, I think, from the Met Office.
Yes.
I had some positive feedback on that. I think one of the questions that all this raises for me is how should we really approach, A, the use of these forecasts, and B, the way in which we verify them. And I think in the subseasonal timescale, you're really often looking for things like weather regime change, and timing of weather regime change and those sorts of things. And so for me, we're sort of caught in an interesting place where I don't think the metrics that we use in NWP are right. Likewise, I'm not sure that the way in which we assess reliability and skill in a seasonal forecast are appropriate either. And I wonder if your group is having a think about what it is this particular class of prediction is seeking to deliver, and therefore how you should assess A, the suitability of the model, but B, the usefulness or skill of the forecast?
I think that's an excellent question, and we are discussing metrics and how best. To first order, we're actually, because we're focused on the CPC operational suite, we're focused on their standard verification aspect. But I think that the point you're making is very important and one that we really do need to discuss as we move forward, because you're right, we do need to think carefully about how we verify these forecasts.
Predictability is, of course, always leading the way for predictions. And I recall von Neumann said when he opened probably the first conference on climate in 1955 that this is the most difficult of all. When you have a problem with both an initial value problem and the problem of physics or dynamics. So my question is to you, having been working with this now and obtained this interesting result, where do you see the main problems are? Are they in the initial value or are they in the physics?
Well, there's no question that physics is a problem, and also the issue of convection is a fundamental issue, and I think Christina is actually going to talk about superparameterization, and I think that that's a really promising aspect. I have to say, my undergraduate degree is meteorology and computer science, so I was very moved by von Neumann when I read that, and I thought this is a really exciting challenge. I think, but initial conditions are very important, and there's a lot of progress in data assimilation that I think can benefit as well. Yes.
I just wanted to comment on the regime change aspect. It's also a hark back to Dennis Hartmann's talk earlier on the winter problem, is that I had no idea, even a couple of years ago, that how much the freezing point of water over land acts as a climate switch. How when you get a snow surface, the temperature drops 10 Celsius, plus or minus 1, and that switches you from a regime where you're vertically coupled in an unstable boundary layer with a shortwave cloud forcing determining the surface coupling to long-wave cloud forcing with a stable boundary layer where everything is only radiatively coupled. And that transition and how well we represent it in these models is fundamental to getting the lock-in of our winter climate regimes that we've seen in the last couple of years, and we should pay some more attention to that.
Thank you.